Hi there, I'm Ryan, an mlpack maintainer. In this video, I want to show how mlpack's command line bindings can be used to build a simple data science workflow. I'm going to assume that you have mlpack already set up and installed on your system. If not, see the documentation or the other videos about that process. And if you're interested in using mlpack from C++ or Python or another language, there are also videos for those use cases. Alright, let's open a terminal and dig in. Okay, so first, let's pick a machine learning task that we want to solve with mlpack's command line bindings. And to do that, I've pulled up the UCI machine learning repository website, and I'm looking at the Higgs dataset. So this is a pretty large dataset. It's 11 million points, and our task is classification. So there are 21 features with which we're supposed to predict whether or not a given row produces a Higgs boson or does not. So we can just click download over here, and it's a little on the large side, but that'll give us a zip file. So let's go ahead and download it, and then we'll take a look at that zip file. Once the file is downloaded, you can see we downloaded higgs.zip, and you can also see it's pretty big. It's 2.7 gigs. We can unzip it to get the actual source file, which amusingly is itself gzipped. So once we unzip it, we'll also need to unzip it. And that will take just a second or two, or three, because again, it is a fairly large file. Okay, now that that's done, we can see that we have a file higgs.csv, which is now uncompressed to 7.5 gigs. And it has this pretty simple CSV format, although that didn't print very well. So let's actually just take a look at the first line. So it's all text encoded floating point numbers, and the first number is the label, either 1 or 0, so this is written very inefficiently in this file. And then here are all the features that we need to predict with. So we can do some very simple command line data science. Let's just see how many of each class we have. So I'm just going to use awk, separating on commas, print the first thing before the comma, and then count how many of each thing we have. And again, it's a 7.5 gig file. This will take a second or two, but this will show us how many points we have with label 0 and how many points we have with label 1. Okay, so we have 5.1 million non-Higgs boson events, and we have 5.8 million Higgs boson events. Okay, so that's a good first look at the data. Now let's take a look at how we can use it with mlpack. So because mlpack's command line bindings are already installed, I can type mlpack _ and I can see all of the different machine learning methods that we have installed and available to us. Now I'm just going to pick here, let's pick mlpack decision tree. So let's take a look, what do we need from mlpack decision tree to actually do the prediction? So I'll scroll up a little bit, and we got a lot of options. And there's a lot of documentation. But here's an example usage. We could call mlpack decision tree, and we pass in a training file and we pass in a labels file. And then we can save the model. And we can do some other things like print the training accuracy. So the expectation here is that the training data and the labels are separate. So we can do this fairly easily. If I just print, and here we can see, if I just print the first field in the file, I just get the labels, right? So I could just cat this to higgs.labels.csv. And so this will give me a file that only has the labels in it, and then all we'll need to do is remove the labels from the higgs.csv file. And so I can actually kind of write a slightly more complicated awk program. Awk is not a commonly used data science utility, but I tend to find it actually fairly useful. For I is 2, I is less than the number of fields. Okay, printf, print the field, and then we have to print the last one. A new line. Let's make sure this works right. Only want the first line. Yep, there are all of our fields. So now we can just put this in higs.data.csv. With that finished, we have the data set split into a file that contains the data and a file that contains the label, which is what mlpack needs. Now, as another step in our data science pipeline, it would be a really good idea to split the data set into a training set and a test set. So for this, we have the mlpack preprocess split program. And so I can run the help here, and we can see how to run this. And there's an example there, but in this case, it's actually easier to just take a look at the input options. So we'll need the data matrix as the input file. We'll need the input labels, and then we'll specify where to store the test data, where to store the training data, and the percentage of the data set that we want to keep as a test set. So the input file is the data. The input labels are the labels. The training file can be higs.train.data.csv with the training labels -lowercase l higs.train.labels.csv, and I'll do the same for the test files. So higs.test.data.csv and higs.test.labels.csv. And as for the ratio, let's hold out 25%, so a quarter of the data as the test set. And then let's just specify the -verbose option so we get things printed on the screen. So mlpack's command line bindings will tell us what they're doing, how long each step takes, what the size of the loaded data is, and things along these lines. So I'm going to skip ahead because we're working with such large data. This doesn't happen immediately, but I'm going to skip ahead until the command is done, and then we can take a look at what the output was. Okay, now that that's finished, we can take a look at the output. So we can see that mlpack has told us it's loaded the data, it split the data into a training and a test set of the sizes that we wanted, and then it saved the output to CSVs. It also tells us how long things took. Now, I want to point out that loading the data took about a minute, and saving it took over a minute. The reason for this is that CSV is actually a pretty inefficient format. So while I'm using it in this video, you might want to consider using the Armadillo binary format or any of the other formats like HDF5 that are much more efficient to read and also to store on disk that mlpack supports. So you can see the documentation for more details on that. But I'll just go ahead and continue using CSVs here. So now let's actually train a model with mlpack decision tree. So I'm going to type --help to get the help here, and I'm not going to look too close. There's a lot there, but what I'm actually just going to do, I'm going to take a look at, here's an example in here, and I'm just going to steal this command. Right? This example just trains a decision tree with a minimum leaf size on some data, and it saves the output model to tree.bin. So let's paste that in, and then I'm going to go ahead and modify it. So starting from the end, we'll also make it on one line here because it didn't paste very nicely. That's okay. So tree.bin, we can still use that for the output. But now our labels file is called higs.train.labels.csv, so what we just made, and our training file is called higs.train.data.csv, not arf. We could use arf if we actually had categorical data, but here these are all just floating point numbers, so we don't need that. Okay, so there's our command. I also want to go back to the end and add -v so we can see what gets printed. Now this could take a minute or two. It'll take at least a minute to load the data set. So I'm going to go ahead and skip to the end, and then we can see what we got. Okay, that's finished, so we can take a look. We now have a model saved to tree.bin, and that training process took about 3 minutes to load all the data and about 10 minutes total, so 6 minutes for training, which is not so bad for 11 million points. On the training set, it gets about 80% accuracy, but now we want to see how does it do on the test set. So let's go back to the decision tree help, and let's take a look. We have an option that lets us load an input model file. So this is a pre-trained decision tree. So I'll start typing out the command here. What we want to do is we want to compute how's it going to do on the test set. So -m tree.bin, that's our saved tree, And then we can pass in, I can see it here, our test file and our test labels. So -T higs.test.data, and then pass in the test labels too, higs.test.labels. And what else do we want? Let's do verbose. And then let's use these outputs here that allow us to save class predictions and the class probabilities, right? Because both of those could be useful if you're building a whole data science pipeline. So let's say test_predictions.csv and then test_probabilities.csv and -v to see it in verbose mode. And we'll see what this gives us. Okay, that's finished. And if we take a look at the output, we can see what we are looking for, which is that the test data gets loaded, and then the program computes the accuracy on the test set, which here is about 70%. And given that the training set accuracy was about 80%, we're probably overfitting a little bit. So we might want to consider changing some of the hyperparameters for our tree. But there are lots of options for that, like minimum gain split, minimum leaf size. And you can find all of that on the documentation, which I'll show in just a second, after we take a look at the other two output files that we've got here, which are test predictions and test probabilities. So the test predictions file, I'll just look at the first 10 lines, contains the class prediction for each point. So the first line, 0, is going to be the prediction for the first line in higs.test.data.csv, right? So there is the data, and that data gets predicted with our tree as having class 0. Now, the other file is test probabilities, and this gives us the model's probability for each class. So for this first point here, our predicted probabilities are 0.53 for class 0 and 0.46 for class 1. So the classifier wasn't very confident about this one. Now the next point has probabilities of 1 and 0, so the classifier was very confident about that point. So you could use these to create, say, an ROC curve or to tune your classifier or things like this, or you could just use these as direct classifications. Either way works. So now let's take a look. I've been using mlpack decision tree -- help to get documentation through this little example, but this is also on the mlpack website. So let's go back to our web browser. Okay, and I'm going to open a new tab and I'm going to go to mlpack.org. Okay, when I'm on the website, I can click on the documentation. And now, the documentation by default, since mlpack is a C++ library, is for the C++ API. But we can scroll down here, we can minimize this, and we can see the binding API section. We can extend that. And so we can go here and we can click on CLI binding documentation. This gives us all the documentation for mlpack's bindings. And this split into classification, regression, clustering, geometry. I can expand these, so I'll just click all of them so we can take a look at what's there. So these are all of the command line programs that you have access to when mlpack is built and installed. So for instance, preprocess split here. Here is the documentation. Looks very much the same as if you type -- help, but it can be nicer to have it on a website. So you can scroll through that. Similarly, we can scroll up and find mlpack decision tree, and we can see all of the options that we have, right? So some of these, like input model file, we just used test file, test labels file, but there's also things like hyperparameters you can tune, specifically these 3. And I think there might be more in here, that you can tune how the decision tree actually works. So that's about all I was hoping to show today. There are lots more command line programs that you can use, and you can build a much more complicated data science pipeline with mlpack's command line bindings, but that's just one example. So I hope that this was helpful for you, and if you have any questions, feel free to consult the documentation like I just showed, or open an issue on GitHub if you have any problems. Thanks for watching.